Cool, welcome to the dev stream, and yeah, so jump instructions. Let me explain what a jump instruction is real quick. Basically, please tell me this side is muted. Yes, it's muted, cool. So, basically what a jump instruction is let's say you have a set of instructions, right? Like you have an add, right? Then you have, like, I don't know, you have, what else do we got in here? You have an add, you have a load, right? So these are just standard instructions you have, right? What a jump instruction is if you have a jump instruction, it'll just go over here, right? So that's all a jump instruction does. And so if you have like a while loop, I don't know, while, let's just say true, because then we don't have a branch. Then we can just say a equals a plus 1, and let's just say that's our entire branch. That would compile down into add, let's say this is at position 0, right? Add I, and then x1, comma 10, comma x1, right? So we're adding, not 10, whatever, we'll make this 10. We'll add 10, we're adding 10, and then at position 4, because this is 5, and each one of these is 4 long, we'd have jump to position 0. And so this is just your while loop. And so this is all a jump instruction does, and that's what it, yeah, and that's all it does. Cool, now we have that. We are going to implement that into our CPU. So, zoom in here a little bit more. Cool, so we have our simulated CPU over here. And so what we're going to be doing here is we're just going to keep going, right? So we're gonna add a instruction like pointer, basically. So what we're going to do is we're going to add a new register. Hold on. And so this register is going to store just our current instruction, right? So wires here, and then a register that just stores our instruction pointer. So instruction pointer. Yeah, I'll use underscore. Nah. Pointer. I'll use my standard way. Instruction pointer, and this is just going to be with -1 colon 0, right? And so that's going to be our instruction pointer. Cool. Now we have that. What we need to do is we need to okay, so this is our CPU. What do we? Right, so we have an instruction pointer. We should be able to feed it information from memory, right? So CPU test bench, right? So we're gonna have artificial memory, basically. So time instruction equals this. No, what we're gonna do is we're gonna store these instructions in a list, and then based on information that is given, so register instruction is this. We will set. Yeah, we'll just have them as, okay. How do I set up just like arbitrary list of data? Because I just want to arbitrarily set up these things so that we can do like jumps and whatnot, right? But we have to be reading from a list. So I have to figure that. Hold on, let's Verilog. What's the word? Verilog memory. Vector arrays, Verilog arrays and memories. Yes. So Verilog array. Register is a scalar array of depth 12, each 1 bit wide, 8 bits wide, and a depth of 4. Okay. Cool. So, and accessing is that. Okay, cool. So what we need to do is I'll just set instructions, and instructions is going to have size, I don't know, let's set it 64 long, and we're going to do that, right? And how do you, that's 2D, we don't care about 2D arrays. Yeah, so we have that, and then we just have to, yeah, okay, instructions of 0, and we're going to set that equal to, they use a register here, right? Yeah, registers work. All elements can't be assigned in a single go. Okay, so you can't assign them all in a single go. Registers, yeah, okay, that's instructions of 0 is, hold on, copy paste this here, and then let's just edit it, right? Because we're in the business of copy pasting our stuff and then editing it. Instructions of 0 equals that. Okay, hold on. There's gotta be a better way to do this. Hold on. Hold on, let me... What if I just copy all of this? So let me... Okay, cool. So we have this. And then colon percent sign s slash hashtag space time instruct time space instruction space equals, and then we're going to replace it. Yeah, we're going to replace this with instruction of... I'll just keep this in as 0. No, okay. I'll just keep that in 0 and manually edit it. Equals. And then... Cool. And so that replaced all of them. Which is actually fine. We don't actually care about the rest of these. Because we're going down this route now. Okay, cool. There we go. And so then we're just gonna... We're setting up all of the instructions. And I'm setting it at 64 just so, I don't know, we have enough space. I could set this up as like a massive list of instructions, but I don't particularly care about that. Is that 3? 1, 2, 3. Oh my god. Because of that? Okay, cool, whatever. And then we're just gonna... 1, 2, 3, 4, 5, 6, 7. What is going on here? 8, 9. Okay, so we only had 10 instructions before. Cool. And then for instruction of 10, let's set it up as a jump instruction, right? So, where are we? We're here. So, where is jump? Where is the jump instruction? Jump and link? No, I don't want to do jump and link. I just want to jump. Oh, I guess jump and link is... Yeah, because they put this in the register. Hold on. Yeah, RD is PC plus 4. PC plus equals immediate. Okay. Cool. So we're putting this in a register. Okay. So I'll put that into... I'll probably make my register thing actually bigger first. So I will... Hold on. Let me edit. Nah, we're not going to do jump yet. We're going to make this work with this style of instruction, and then we're going to do that, right? Register, that contains our instruction pointer. And so register regs has that. Instruction decode ID. ALU, yep. So what we need to do, input instruction, yes. And then we need an output. Output, and this is going to be our instruction pointer, underscore pointer. And I'm going to set that up as an output. Instruction pointer. Instruction underscore pointer. Cool, so there we go. There we have it. And so now what we... Yeah, we just have to keep going here, right? So we have instruction pointer, the instruction, input. Cool. So, yeah, and so now... Hold on. Yes. So we have an instruction pointer. And that takes the input, right? And so in our test bench, we will take the instruction pointer and just read the value of instructions. We're not going to be able to write any instructions, but that's fine. We're Harvard architecturing this. We're not doing von Neumann architecture. We're Harvard architecturing this. So, yes. So instruction is an input. Yep. Instruction pointer is an output. Cool. And so in the CPU test bench, what we're going to do is we're going to basically set it up so that instruction should not be a register. Wire instruction instruction, and obviously we have to have the size of width -1, right? So we need to set the size of the instruction. So we set instruction. So we're going to do assign instruction equals instructions of and we're gonna pull out the instruction pointer. Cool. And so then from here, we are going to just I'm just gonna set up another wire. Instruction underscore BTR, and we're going to feed that in here. Instruction BTR. Cool. So then compile it. Errors. There we go. CPU v19. Probably because I forgot a semicolon. Yes, forgot a semicolon. Whoopsies. Cool. 10. Okay, nvim CPU catchbench.v, and so line 10. Huh. Oh my god, I understand now. Because these all say instructions or instructions. There we go. Cool. Invalid module instantiation. CPU testbench.v of 10. Invalid instantiation. Huh? Verilog. If 0 is... Yeah, should be correct. B. We are doing it in binary, yes. What is... Invalid... Sorry. Warning. Extra digits given for size binary constant. Okay, what is the size here? It's size width minus 1. So we should expect 32 bits, right? Hold on. Syntax invalidization, huh? That has a nice thing. Okay. Line 11. Invalid module initialization. Extra digits given for... I don't care about that. Invalid module initialization. What does this mean? Well, let me count this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So that's 20. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2. Yeah, that's 32. That is 32. This is correct. We do have 32. Cool. Assign that to be that. Yes. Invalid module initialization. How do I initialize stuff in registers? I just set equals 0. I just say equals, because that's the initialization. Okay, hold on. Instructions is this. What if I write assign? Oh, assign is correct. Okay. And yeah, okay, so I just assign yank word paste, and I'm just gonna keep doing this until there we go. Compile. Cool. 11. Error. Reg instructions cannot be driven by primitives or continuous assignment. Okay. So I can't use assign. Okay, cool. So that's insane. Instruction pointer. Oh my god. Did I set the size of instruction pointer? No, instruction pointer is the right size. Instruction pointer of CPU expects 32 bits. Instruction in yank word. Typing is hard, you know? Okay, extra invalid module instantiation. How is this invalid? I do not get it. Yeah, okay. Okay, display mem1 is this, yeah. Sure. Okay. Huh. Okay, hold on. So, 8 HAA, you have HDD, you have what? All elements can't be assigned in a single go. Assign A2 to index 0. What is the 8? Oh my god, do we have to tell it 32? 32, 32, 32. Invalid module initialization. Line 11 syntax error. Instructions of 0. Hold on, at this point, I'm just gonna feed this into an AI. Like, let's be real. I am not. Let's go to our good friend. Let's paste. Copy. Paste. And then yoink these. And let's see what the AI says. Let's figure out what it's telling me. Up, I said the thinking. What's its thinking saying? Test parameters displayed. The issue is that you're trying to initialize instructions array outside of a preview block, like initial always. Ah, so we have to say as initial, begin, and end. Ah, that checks out. That checks out actually. Initial. End. So initial, begin, and an end. Cool. Compile. Ah! It doesn't actually finish. In Vim CPU test bench. Cool, so we have the clock. Okay. Cool. So 0, 1, 0, 1, it's all set to 0. These numbers are too big. How do I initial begin? Hold on. I'll just have this go for like 10 cycles. Always. Hold on. Initial begin. Hashtag 1 CLK equals not CLK. End. And then I'll just go. I'll just have that go for 16. Clock. Okay. Why is it just continuously running? We're not doing anything here. Oh, I should probably do like a finish instruction. Hold on, let's go back to here and let's figure it out. Simulation. Yes. Yeah, okay, we're here. Freeze processor. Okay. So, always, where is the in main? Dollar finish. Yes, okay, I got it now. Dollar finish. Oh, hold on, I should compile it first. Line 31 malformed. Okay, oh, I forgot the semicolons. Whoopsies. /test. There we go. So we go, and we're not actually doing anything. Okay. Cool. Okay. So, what is going on here? Why are we not running the first instruction? Hold on. Let's nvim cpu.v. Let's monitor the instruction. And let's let's just set up instruction, and let's monitor the value inside of our instruction. And get rid of the period, of course. You know how it is. Instruction. We're not getting any instruction. Okay. Cool. So we have instructions. Assign instructions. Instructions of instruction pointer. Okay. Oh, what is the value of instruction? nvim cpu.v. Okay. Instruction pointer. I can probably default it to 0. Dot / compile / test. Oh, there we. No, instruction's still empty. Nvim CPU testbench.v. Let's not monitor output. Let's monitor the instruction pointer. Instruction PTR. And let me yoink this so I don't make any spelling mistakes. Yank wood. Paste. Comma. And paste. / compile / test. Cool. I should probably nvim cpu.v. And let me comment these lines out again. Because I think if we get the instruction, we're actually going to be like all fine, right? Like I think that's probably the big issue here. Let's compile / test. Instruction pointer is nothing. Instruction pointer is, I mean, we set it to be 0. Oh, we never write assign in instruction pointer equals instruction pointer. Cool. Let's just compile /test. 15. We're not incrementing it. That makes sense. NVIM CPU. So again, because of the time we have going on here, we should when we're done the instruction, we should increment our instruction pointer by 4. Hold on. NVIM. What is it? cb.v. Okay. These should be going up by 4 each time. 0, 4, 8, 16, 20, 24. Because that's just how RISC-V works, right? So we're gonna have it do this. 36, 40. Cool. And so when we're doing instruction pointer, so we just have to set instruction pointer equals instruction pointer plus 4. And so obviously we have the clock cycle that goes up and then down. And so on the negative edge, hold on. Instruction pointer plus equals 4. Is that legal? Let's compile it. 31, 11, 31. Okay. So what's going on here is our starting instruction pointer. Because the first clock edge is positive, and so. Huh? Instruction pointer, why is it starting out at 8 instead of 4? Huh? Hold on, let's run a test a few more times. No, it's deterministic, okay. So 0, it should be starting out at 0, but we can clearly see it's starting out at 4. So this implies that, oh, hold on. Clock starts at 0. Rising edge, and then we, huh? Hold on, I need to think about this for a second. Okay, what if I just set instruction pointer to be -4? Will we see good behavior? No, we're not. Oh no, I had to compile first. Whoopsies. Compile .test. We are seeing good behavior now. Okay, sure. Yeah, I mean, we're incrementing by 4 on the negative edge of the clock. If it goes from non-existent to negative edge, it, like, drops. So when we, like, start it up, we have to... Yeah, okay, that checks out now. That checks out now. Yeah. Cool. So we have our list of instructions. And so then what we have to do is we have to support jump instructions, basically. What are the jump instructions in RISC-V? Jump and link register. Standard extensions. We're not doing floating point. And we're not doing atomic instructions here. Like, that's just not happening. Compressed. Oh, we're not doing 16-bit. And pseudo instructions, I assume JMP is one of them. J. Okay, and okay, sure. So we're gonna implement jump and link. No, what we're gonna do now is we're gonna implement more registers. Because theoretically, this one supports way more registers, but we're not having it do that. So, I'll set up each one on a separate line. Paste, paste, paste. X1, X2, X3, X4. Cool. Because we have 32, right? So, X5, and let's just go up to X8, 5, 6, 7, 8. Let's support every single register, right? So up to 31. So there's 8, 16, 24, 32. I'm just gonna do this. Reg X 31 colon 0. 30 colon 0 because we only have X1 is, and I'll just do X of 1, X of 1, X of 2, X of 2, X of 3, X of 3. I'll do 31 to 0. But that makes X0 writable instruction, which I don't want actually. Oh, I'll just set it up here. If reg W greater than 0, X of reg W is set as, yeah, data W. Cool. And then out. I don't have to do all this. I can just straight up read from the registers, right? So, oh, I can't do the just equals 0. Nah, whatever. X of reg A, and then out B is X of reg B. Wow, this is so much simpler. Cool. So we have this, and we have the width. Let's make sure this still works. Assignment, yeah, okay, yeah, this equals 0 is illegal. Let's go to our nice search. How do I edit a whole bunch of them simultaneously? I just straight up have a for loop. Okay. Sure. Initial, begin, and I'm just gonna straight up have a for loop here. For int I equals 0, I less than 32 because we're running this 32 times. I plus equals 1, right? Oh, I just begin and end. Begin, end, X of I equal, not 1, I equals 0. Now we compile it. Incomprehensible for loop. Probably because no space. For begin, yeah. The register is what? Initial begin. We have a nice for loop with a thing. Oh, I can't just do plus equals 1. No, I can do plus equals 1. Int I equals 0. You know this? Huh? 15. Yeah, okay. So this for loop is bad, apparently. For int I equals 0. I'll do I equals I plus 1. This should work. Okay. Okay. Incomprehensible for loop. X of I equals 0. Begin. Yeah, okay, this is like fine. And yeah, this feels like it should be fine. Yeah, okay, I know what memory is. I know what memory is. I know how this works. I know how this works. Cool. So I less than 32. Int I equals 0. Huh. Okay, how am I gonna make this work? I know what we're gonna do. we're gonna go to our AI assistant again. And then, whoopsies. All right, what is the error here? All right, Gemini Flash 2. Gemini 2.0 Flash thinking experimental 121. There's no new one. Okay. Syntax error. Yeah. Is older. Do not allow variable declaration in the for loop installation. Generates what I. It's okay. So we just have to say integer I. Okay. Sure. I'm working on integer I. Cool. So we're working with C here. In one, syntax error in variable list. Integer I. I just needed to go through 32 times. I don't want to have the same line a whole bunch. Complete example. Yeah. Okay. I equals 0. Oh, semicolon. There's the issue. Variable declaration unnamed block requires system verilog. Do I not have system verilog? Sure, I'll move it up here. Just random integer. And then compile. Okay. We still chilling? 15, 31, 11. Yeah, we're still chilling. We are still very much chilling. I should probably print out all of the yeah, I should probably print out all of the memory addresses, but I don't particularly care because I'm only using like 3 of them. Just a good idea to have all of the memory addresses available. Yeah, cool. Now we implement jump instructions. Nvim instruction decode.v. So let's just add a whole bunch of outputs to this, because I know I probably will need them. And so I should add the should jump might need branch, and then we do control logic there. Well, I mean, let's turn on the jump, and then I'll just go out down here. Output jump, and then we just keep going. So I want to jump. I want to do branch. Yeah, I'll do branch. Output branch. Next, we need the format. There's 6 formats. 1, 2, 3, 4, 5, 6. Right, 6 formats. I will. Yeah, I think I'm just gonna add another number, which is format of the instruction, and so then I will say output format, and this is going to be how many I'll just have it as a whatever, it's wires. I don't particularly care about silicon area right now because the theoretical CPU, nobody cares about silicon area. The theoretical CPU doesn't exist. Cool. So yeah, I don't care about that. Cool. So jump. Where is the fancy stuff in the jump instruction? We have, it's this bit over here. Because, okay, so the last 2 being 1, 1 is standard. This is the, so this jump and Louis. Okay, that's wild. We're just checking this bit for branch and jump. Yeah, okay. So assign branch. So wait, we have to assign the jump and link registers to be. It's just this. The jump would be this and this ANDed together, right? So this would be 0, 1. It would be, so jump equals instruction, and so obviously the opcode is 6 to 0. So I'll just assign it here. Here we go. Assign jump equals opcode of 2, and I should probably use this fan. That's probably correct. and opcode of 6. And we just have an AND gate in there, very nice. Branch would be, so branch is, this is on, and this is off, and this is off. Okay, so 2 and 4 off, 6 is on. So 2 and 4 are off. This tilde is not, I assume. And opcode of 6 is on. And so I should... I mean, I don't need to bracket this. This should just work. And then obviously we have format. I'm not going to deal with that just yet because I don't want to. Jump and branch. So nvim cpu.v. And so I'll just say, I'll go wire down here. Wire jump, comma, branch. And then outside of instruction decode, I'll do jump, branch. Always on the negative edge of the clock. If jump, then right B is our... Hold on, is it? Hold on. Jump and link. PC plus 4, PC plus equals the immediate. Okay, so we just do immediate, so... PC plus 4... Oh, RD is PC plus 4. Okay. So, RD... So the write back value is PC plus 4. So then... Let's go... Instruction pointer plus equals 4. End. Whatever. So instruction pointer plus equals 4. Then what we do is if jump, then we do the swap. So yep, if jump. I forget how to do an if statement in here. Nvim lu.v, we have if statements? No. No, we do not have if statements. CPU test bench. We got any if statements here? No? No if statements. Okay. Let's go back to the Verilog. If, parentheses, begin, end. Okay, there we go. If jump, begin, end. This should be here. Begin, end. Cool. So if jump, then what we do is negative edge of the clock. We write back. Yeah, so I should probably turn on a write back in here. Hold on. Write back. Yeah. If jump, then... Well, that one outputs right back, so we have it as on, right? And jump also implies right back, right? So that's whatever. If we are jumping... What are we doing if we're jumping? If we're jumping, what we're doing is we're writing the value back. So, val write equals instruction pointer instruction pointer equals immediate. What's immediate is just func7 comma rs2. I am going to set that as an actual value, but whatever. Cool. Slash compile. Val write is not a valid L value. Val write here is set as a wire. Checks out. Val write. Assign val write to be the instruction point. Hold on, I need the... There. Cool. Assign val right to be the instruction pointer. 34, syntax and assignment value, L value, 34. 34. Syntax error? I just use an equals there. Val right is not, val right is a wire. 24, wrong number of ports. I'll just delete right back here and then we'll deal with it soon. Cause, yeah. Let's compile. Okay, val right here is declared as a wire. So it's a wire, so we take it from instruction pointer. Syntax error in line 34. Syntax in assignment statement L value. Hold on, how did I do this? What is this? Registers dot v is wire heavy? No, nvim instruction decode. Assign just blank equals blank. Okay, but that's what I was doing. Assign blank equals blank. Oh, we need an else. Begin and end. Oh, hold on. So the value we're writing back. Okay. I'll just set up val right 2, VL2. And in the registers, val right, VL2. Down here, VL2 is the instruction pointer. VL2. Otherwise, it's VL2 is val right. Val right. So this is just a mux switch. VL2 is declared as a wire. Why can it not be a wire? I want a mux. Oh. Okay, sure. Assign VL2 is equal to, and then based on jump, what we do is we set up, if jump is true, it's instruction pointer plus 4, and if it's not true, it's val right. Not CL2, VL2. Cool. So we always set up it by 4. Otherwise, we do whatever. 31 and 29. It's because I forgot a semicolon. Oh wow. Does this still work? That bit still works. Cool. So what we need to do here is nvim CPU testbench.v. Cool. And so now we need an I format. Yep, add I. Let's yoink this add I in 8. And I don't know, let's paste it down here under 40. And so 44. And this is going to be a jump instruction. So instead of add I, we have to generate the jump instruction. So jump and link. We're going to do a jump and link. And so it's just RD and the immediate, right? Because it's I format. Well, effectively I format. Where is it? Jump and link. Yep. RD and the offset. So, hold on. Yep. Jump and link. We're going to write this into... Let's write into X4. I don't particularly care. And offset. Ugh. Okay, so... let's just go -5. No. I mean, we're writing the number directly back, right? So, let's just go to instruction number 16. Cool. Now we have to manually generate it. Amazing. So, jump and link. 1, so 1, 1, 1, 1, and then 0, 1, 1. So that's the first 7. Then we're looking for RD. And so the RD here is X4. So 1, 0, 0. And so we have 1, 2, 3, 4, 5. Cool. So now we're on to func3. The func3 here is we don't care. So I'll leave it as zeros. 1, 2, 3. Then we have RS1. This is J format. J format, the rest of this is literally just the immediate. Okay. So then we're going to 16, right? Hold on, let me count this again. 7, 1, 2, 3, 4, 5, and 16. So 1, 2, 4, 8, 16, and the rest of this is 0. Cool. And so let me nvim function decode.v jump branch. Let's just go I dash immediate, and then I can't do that. I immediate. I'll do immediate I. I'll do immediate I. We'll do immediate I here. Immediate I. Then what we do is immediate J. Cool. So output, and then so immediate I is 12, 11 colon 0. Immediate I, and an immediate J is, what is this order? Huh? Oh, right, because it's, okay. Yeah, I get it. It's 20 colon, it's, yeah, okay. Yeah, I remember this. This is unfortunate. Cool. So, assign immediate I, and that's literally just instruction of, and then this is just 31 to 20. 31 to 20. Assign immediate J to be instruction of, hold on. So first we have the first bit, so it's 31 colon 31. I'm just going to turn on the concatenation operator here. Then we go instruction of 19 to 12. Sure, it's immediate of 19 to 12 here. Then immediate of 11 is 20. Of 20, and then we have instruction of the rest. So it's 30 to 21. Correct? Yeah, it should be 30 to 21. Yeah, because that's 20. Yeah. And then a 0. Nvim cpu.v, and so now we just need a few more values, a few more wires. Wire immediate I, immediate J, and then at the end of here, immediate I, immediate J. Oh, cast lock's on. There we go. Immediate I, immediate J. And so instead of doing this, I'll just write immediate I. And instead of doing this, I'll write immediate J. Cool. In Vim CPU testbed, I'll do that, and then I'll just do finish after like 60 cycles. $finish after 60 cycles. Process compile. Okay, there we go. Few warnings. We should fix the warnings. Instruction decode. Concatenate operation. SD0 has indefinite width. Okay. So I cancel that to 0. Sure. I don't know. I'll just do this. Reg 0 colon 0, and then 0 of 0 equals 0, and then I'll just 0. Literally just a 0. Syntax error in line 12. What? Oh. Okay, you know what? I don't particularly care here. We are not doing that. What is gonna you do? We're gonna do that. Line 20. Okay. Okay, sure. Let's do a binary number then. Compile it. Immediate I of instruction got 12 bits. It expects 12 got 1. Immediate J. Oh, CPU.v. 12 and 21. Yep. Wire 11:0. Wire 20:0. Syntax error in line 17. That's because I put a comma instead of a semicolon. Whoopsie doo. Cool. Line instruction decode line 20. It has indefinite width. Okay. Sure. NVIM okay, what do I know is going to be 0 in a jump instruction? I know 0 is going to be instruction of, and then we know 0 is going to be here. So 0, 1, 2, 3, 4. Instruction of 4:4. Whatever. That's just compile, that's test. There we go. Instruction pointer 65,000. Because I moved that over way too many zeros. NVIM CPU test bed, yep. Cool. No, it might be because the instruction decode is wrong. Yes. So if I want to put it in the right spot, oh my god. Okay, so this is 20. So, right? Then 10, 9, 8, 7, 6, 5, 4. Oh, there we go. Now we're nice and looping. Nice! Okay, so what's actually going on here? I don't actually know what instructions being 44. And then we're jumping down to 16. And we're jumping down to 16. This is good. This is actually good. We're jumping properly. Jump and link works. Cool. Now, what else do we have? We have jump and link register. RD PC equals RS1 plus immediate. So we could do Jalo? Huh? Maybe. Perchance. And that's I format. I do want to support this one though. So RD is RS1 plus immediate. Okay. And when we do instruction decode, I could just have like an enum that sets up here. And that could work, but you know, I also don't want to do significant big extend zero extension nonsense, right? But that's just an ALU problem, right? That's not a real full problem. But yeah, so I just had to like kind of keep going there, right? So I just had to yeah, I just had to I'm gonna realize I have no clue what I'm trying to do here. I want to support jump and link register, right? And then all of the J jump stuff is done, and then it's on to branching, right? B format has its own goddamn immediate setup. Cool. Yeah, sure. So I should probably write on NVIM CPU test bench. Hold on, let me edit this. So instead of writing it into X4, I'll write this into X3. Right? Oh, that's test. Yeah, obviously value of X3 goes kind of insane, but 44. writing 48 into x3. Why are we writing 16 is huh? Why are we writing 48 into x3? And then we're writing back. Oh, it's going to be writing back some random value. Ooh. Okay, so wait, on the way back, val right, if jump is in fact true from the instruction, so when the thing turns on, it will set up VL2 to be correct, right? Instruction pointer +4 or val right. So, oh, it is 48. 48 is correct. 48 is the previous one. No, this is correct. 48 is the next one. So we can jump back to it if we want. Yes. So if I... Okay, this is actually pretty nice. So if I'm going to jump link register now. That's, I think, next step. It's implementing jump and link register. Yeah, and then after that, I think I want to end the stream because that'd be a great success. We have jump now. We can, in fact, jump. Jump and link register. Cool. And Vim. Instruction decode.b. How do I do enums? Verilog enums. System Verilog. Yes. Okay, sure. Sure. Instruction decode. Enum. Instruction. Nah, whatever. Whatever. We're not going to do enums. We're gonna go jump and link register. Hold on. So how are we telling it to jump? It's gonna be, I said jump to be true. And so we know jump is true in this case. What we don't know is jump and link register. So assign is Jaller to be opcode of 3. 3, and I'll just put a tilde in front to negate that. Right, so is Jaller. Right, and obviously we're gonna have output is Jaller. Jump branch is Jaller. And then up here, we're just gonna have, because these are all basically free, right? Because it's just wires, right? Obviously, silicon area there, but like whatever, it's just fine. These are gonna be very simple, right? I don't particularly care. Yeah. So we have is Jaller, where you can do jump and link register, and so from here, what we have to do is we have to add is Jaller is Jaller, and at the end of instruction decode, we do immediate j comma is Jaller, right? So it is jump and link register, and then from there so if we're jumping, then we set RD is PC +4. Yep, we do that here. Then if Jaller, we do RS1 plus immediate. So we set that as immediate J. It should be an offset, but whatever. I don't particularly care. If jump, if is Jaller, begin, end, instruction pointer equals, and so it's the value in RS1. Yep, the value in RS1, so val A, because val A is RS1. What is val B RS1? RS1, RS2. Val A, so for add immediate, or val B is RS2. Val B plus immediate I. Else, begin, that, end. Cool. So I will test this. right? So obviously I'm gonna have a jump and link in 48, whatever, and in 44 I'll have a Jala. So we're gonna jump and link register, and so jump and link register. We have the output. Where's the standard notation for Jala here? Where's our pseudo instructions? Pseudo instructions. JALR. So jump register x0. Okay, so x0 we still have a current position in the first one. So let's put that in x3. Sure, let's put the 48 in x3. Then the starting let's put the let's 40 there. Then let's go x3, and then we're going to jump to the immediate is 0. Then I will add I x3 16. So 11 is 1011. Yep, immediate. So we want 16. So this is 8. There we go. There's 16. We're putting 16 into x3. And then jumping link register is a little bit more of an instruction that we have to manually make. So jump and link register is 111 0 0 1 1. Yep. And then for here we go 1 0 0 1 2 3 4 5. Cool. And then to the left of this is I format. So we need func3, which is 0 1 2 3. There's our func3. Then we have rs1, which should be x3, and the immediate is 0. So cool. Let's compile. Port is Jala 12 if instruction code is not declared within module. Output is Jala. I didn't use that there. Compile, yep, .test. Are we still looping around? 44, if we went back to 0. Sure. Hold on. Went up to 44, down to 0, went up to 44, down to 0. Okay, so we should be going down to 16. X3, why does it have 11 in it? Hold on, NVIM CPU test bench. Oh, probably because it's like we wrote 8 there instead of 44, 48, 52. Let's compile, let's test. Cool, so we go up to 48. Why are we still dropping down to 0? We have 16 in x3. So we're clearly not writing that back there too. Probably because I format CPU.v. Hold on, I format. So I format we're not doing immediate I, we're doing val b. Yes, val b. Right, so obviously reading is always on. Opcode of 0. Huh. Opcode of 0. I'm adding a write back here. NVIM instruction decode. I'm going to edit write back here. Write back. And I'll just say output. I'll just add it to here because it's just a one bit thing. Write back. Assign. Write back equals 1. We're always writing back in this instance. We're not like having any instructions. Because branch will not do any write backs. But, you know, whatever. And so wire in here, write back. And so instead of opcode 0, I'll have write back .compile .test. 16. That's a very good sign. We're not writing to this properly. We're writing to instruction pointer. We're not writing to it properly. NVIM cpu.v. Okay, so what's going on with here? If jump begin, yes. Otherwise, it's immediate J, which is wrong in this instance. No, is it? Going to 0. Val B plus immediate I. Dollar display. And then we're just going to display val B. What is in val B? Colon, percent sign, let's just do percent sign 0D. We're just gonna, and then val B. What is in val B? Val B is 0, 0. Okay. Yeah, we have the right value in the register. The CPU. RS1. Okay, hold on. Maybe we are looking for val A here. $16. Okay. Wait, but then how is RS? Hold on. RS1 is in the right spot in all of these, so RS1 is val A. RS2 is val B. It should be val B. Okay, cool. There we go. /test 16. Yep, we're jumping to the right spot. Cool. CPU.v. Cool. Let me delete this print statement. And then let me edit our instructions to be correct here. So add I x031. So instead of 31 here, it should be 16. And instead of x0, 1, 2, 3, 4, 5, 6, 7, RD, oh my god, here, it should be x1. Cool, and so if we still get /compile, /test, are we still getting the whole 0, 16? So we should be adding 16 to x1. nvim CPU .v. Okay, cool. So write back is on. We're writing 16. It's just we are not reading the right value here. What is val A value? In A. No. This should be val A in B. So in A. Cool. That's so jank, but whatever. 0, 31, 11. Yeah, everything else is in fact correct. Cool. So we found a correctness issue here. I'm going to turn off the clock display there so I can make this text a little bit bigger and reggae. Hold on. Let me delete the reg A and the clock so I can make this bigger. Nice and big, just for you guys. Cool. No, I need to make it smaller so I can actually display X4. Nah, I don't really care. Cool. So, we have the registers, we have all of that. I think that's actually a very nice bit of work for today. I will leave it at that. I will see you, one viewer, later. Thank you all for watching. I will see you all next time. Thank you.